Okay, let's start. I'll share my screen. So can you see the screen? You can just type in if you don't wish to speak.
Yes, sir.
Okay, great. So I'll quickly go over what we will mm, talk today, and I mean solve problems today, right? So you know the concept of supremum, right? Supremum, open sets and closed sets. So this is what the problems are all about mostly in the today's tutorial. So you know all these things, or it is you want me to give a quick recap of what all these are? Okay, so let me give quick recap then. So this is the least upper bound. Okay, so let's say there is a set A which is bounded above. That means bounded above means there exists a number um, m such that for all A belongs to A, right? This holds. Okay, and so this A, so we call let's say S to be supremum, small s, if it's an upper bound. It's an upper bound. Okay, and any number say alpha less than S is not upper bound. Okay, it's clear. So let me give you few examples, say 1 to 2. So this is an open one, sorry, closed one and open two. Uh, can you tell what is the supremum of this? Supremum of this set, right? The supremum of this set is 2. Because if any number you pick, 2 minus epsilon, let us say, right? So for very, very small epsilon, let's say 1.999. This is not a lower bound for this set because you can always find a number 1.999999, right? Which is greater than this. Okay. Um, so this is clear, right, Supremum?
Yes, sir.
Okay. And similarly, the other side exists, the infimum, called the greatest lower bound. So in this example, if we say 1 to 2, okay, so 1 is the infimum because I mean that's the greatest lower bound. If you pick any number greater than 1, it will not be a lower bound, because let's say 1 plus epsilon, which is very, very small, 0.00001. Let's you put it this way, right? You can find a number that lies between this and this, right? So there exists a number here in this set, and you are saying this is greater than this. So it's not a lower bound. So that's infimum, the opposite of this thing, supremum. So to know this thing, open sets and closed sets, there are two notions that I need to clearly go over. One is interior point. So another one is limit point. Okay, so interior point is, let's say um, there is a set, let's say call an open ball in R2, right? The so point P is this, we call this point X as interior point. If there exists a radius R, when you draw a ball around X, it should lie completely within the set A. Okay, for every point in A, you should be able to do this. Only then it's sorry, when you're able to do for every point X in A, right? So then it's an open set. So what I mean to say is every point of the set has to be an interior point. Only then the set will be open set. So how do we write this mathematically? If there exists some uh, say d of r of p should contain entirely within this set A. Now I'll describe what is an r of p. X such that distance between X and point P is less than R. R is a positive radius. So basically, this is nothing. This is what I'm describing is just this ball which I have drawn here. So that ball is nothing but, if this is my point P, let's say, now I'll fix a radius R. And if I find such a radius R where each point within this radius lies completely in my set A. So that's what is this, right? Now, if you are able to, such a point is called interior point, and if all the points of the set A are interior point, then A is open set. Okay, and now coming to a limit point. Let's say there is a point, there's a set A, and a point P is a limit point of set A. If you draw if you draw a ball around P, which is not the way I described here, like this, right? And this ball should intersect A, and this intersection cannot be an empty set. It should intersect, the ball should intersect this set A, and that's it, and it should not be empty set. With one more caveat, it should intersect A apart from the point P. Okay, so empty set, uh, this intersection cannot contain p basically. We can subtract p from this. It's clear. I mean, it is might be a bit confusing if you see it for the first time. Um, so basically, it's the thing. Let me draw some pictures that might be helpful. Let's say a point. I am taking a point P on the boundary of this ball, right? No matter if what radius I pick, I draw a ball around this thing. It will intersect my set A. This ball is the original ball is set A. It will intersect this here, right? No matter how small I choose radius, it will intersect at some point of the set A. So this P on the boundary is the limit point of the set A. So inside go, if we go and draw any ball, it will intersect the set A apart from P. Okay, so that's the definition of limit point. Now a set is a closed set if it contains all its limit points. Okay, so limit points of A set A should lie in the set. So this is very abstract definition of closed set. So this is what I want to tell before we start the problem solving session. Any questions on this? I can go over.
Uh, Sir, limit point, can you explain once again?
Yeah. So let's say this, we call this as set A. This is my set A. Now the question is, let's say I pick a point P on boundary. We want to say if this point P is limit point or not. So for this, what you should do is, as per the definition, for every radius around the point P, let's say this radius, it should intersect my set original set A at a place apart from the original point P, right? So where it is intersecting? It is intersecting on all this dotted place, right? So for any radius, this is the case. Now I'll give an example. Let's say the same thing. Ball is there, and there's a point P here. Dot. Is this a limit point? It's not,
No.
because I can draw a radius. I can find some small radius and draw around point P.
Static
It
intersection
doesn't
is empty.
intersect. Yeah. So this is
Yes.
not a limit point.
Yes, fine. Okay, thank you, sir.
And
Got
one
it.
more thing is, the limit point need not belong to the set. So
Okay.
this point is this boundary is there, right? The boundary need not belong to point A, the set A. So if let's say we can call this as an open ball around point P, right? Now I can draw this a dotted ball. That means this set doesn't include the boundary, which is in dots. Okay. But then if I pick any point on this boundary which doesn't belong to set A, it's still a limit point, because draw any radius, it will intersect the into this thing, the points here, right? I can go over this if it's not clear. Why the limit point need not belong to the set?
Yes, sir, it is clear.
It's clear, right? Okay, and Yeah, closed set is what? As set, if a set contains all its limit points, then it's a closed set. Open set is uh, every point of the set should be an interior point. That's an open set. And the supremum, like that's a least upper bound. Okay, so here one more small caveat here is the concept of isolated points. Okay, so let's say this is my set A, and there's a point P. Now B, if I define B as A union P. Okay, so now the set B contains A and it contains this point P. Now, what is the behavior of this point P? This point P belongs to this point P and belongs to B, and this is not a limit point of B, right? Because you can draw a, a point around a small radius and it will not intersect anywhere. So such points are called isolated points. Okay, so closed set can contain isolated points, right? But limit points doesn't capture the isolated points. And so for let's give a concrete example that will clear things. So this is the set 1, 2. So this is a closed set, right? By you can verify the definition. It contains all its limit points. This set 1 and 2. Now, if I do a union, say 3, is this a closed set? This is a closed set or not? Is the question. We know that this is a closed set, yes, for sure. But what about this 3? Singletons are closed sets because it's an isolated point. And I mean the justification for this is let's consider some set S to be 1, 2, 3, and 4. Only 1, 2, 3, 4. Okay, there is nothing else is present in S. Does this set has limit points? Because if you take a point 1 here, you can always draw a small ball around 1 and it will not intersect the set S, right? So anywhere, right? So 1 is not a limit point, so it's an isolated point. Similarly for 2, you can draw a ball and can call it as isolated points, right? So all these are isolated points. So what are the limit points here? It's empty set of limit points is nothing but empty set, right? But empty set belongs to every set, right? Empty set is a subset of every set, so that's why uh, you call this as closed. I mean, sort of by vacuous, but yeah. So set of limit points of S is empty set, and empty set contains S, contained in S. So that's why it's closed set. It's clear why the discrete uh, points are closed.
Yes, sir.
Okay, so let's quickly start solving the problems. Which of the following statements are true? The empty set is neither bounded below nor bounded above. Empty set is bounded below but not bounded above. Basically, it's asking, is empty set bounded above or below or both? Okay, so is the detailed answer. Now, when we call a set uh, A to be bounded, if there exists M such that X is less than or equal to M for all X belongs to A. So this is what we started actually today. By when when we was defining the supremum. And so this means to put it clearly, you should be able to find an M such that all X belongs to A, X should be less than or equal to M, right? So this means for an empty set, there is nothing to find. And there is no X belongs to that A, right? So we take this vacuously true, that there's nothing to check basically. Similarly for bounded below. Okay, so empty set we trivially consider to be bounded above and below. Okay. Now the second question. That's what I was started with today. The supremum and infimum. State whether which of this statement true is true or false. A is 0 1. By the way, A is closed, right? It is closed, and B is also closed. Then for every beta belongs to 1 comma 2, that is a set that is lying between A and B, is a supremum for A and infimum for B. Is this true?
Uh, I think it is true.
No, no. Just recall that supremum is not just any upper bound. It's a least upper bound.
Yes, then no.
Yeah,
Because for 0, 1, 1 is the supremum.
good. Yeah, one is a supremum,
But
and
it
for
does not belong to that open 1 comma 2.
right, right. And similarly, 2 is the infimum for this set B.
Yes, sir.
Okay, so when they exist, one more thing to I forgot to mention, when supremum or infimum exists, it is unique number. Okay. Yeah, I mean it's a detailed solution. You can I'll upload these things. I mean I forgot to upload the last week one, but I'll upload both by Monday.
Okay, sir.
Yeah. So this you should be able to give some counter example easily. State whether true or false a subset A that is contained in reals, I mean one-dimensional real, is closed if and only if A is finite. So what it is saying is, if A is finite, you should tell it is a closed, and if it is a closed, it is saying it is finite. So is this true statement? So we just discussed in detail that every finite set is closed. So one way of the argument is done, right? If A is finite, it is closed. But the other way of the argument, is it true? If a set is closed, it has to be finite.
Not necessary.
Not necessarily, right? It's simply closed 0 to closed 1, right? That's
Yes.
a infinite set and it's closed, right? It's false. Yeah, so state again if this is true or false. There exist two intervals. The nature of the interval is not been said, like open, closed, or whatever, such that there are conditions now. Um, yeah, I mean they are closed actually. I and J are closed, and the intersection of I and J is empty, but I union J is R. Is this true? Can it happen? So one more thing I again forgot to mention between the open set and closed set thing is, um, if A is open, A complement is closed. So using that, we can solve this. Can you can just give it a try for 1 or 2, maybe a minute, then I'll start. I'll explain. Okay. So here is sorry, my system got um, a restart. So can you hear me now?
Yes, sir.
Yeah, let me share my screen again. Right. So here's the thing, right? I and J have to be closed. But then it is said that I union J is R and I intersection J is empty. Okay, is such a thing possible in the first place, right? These are closed intervals. So our entire space is R. Okay, we are not looking anything beyond R. Okay. So now let's assume I is minus infinity to A. Yeah. It cannot we cannot write that. That's what I am just trying to prove here. Um. So right. So now this is I. You know what is J? Can you think of what can be J to satisfy this thing? Right. J has to be A to infinity. Right. So in terms of J, right, how can we write J in terms of I? This is nothing but I complement actually, right? Complement is done with respect to the underlying ambient space, that is R, that is R minus I. Okay, now we started with an assumption that I is closed, and it is closed if you can check this, right? And we ended up getting J to be I complement, right? But if this is closed and this is open, J is open, right? If I is open, um, I is closed, I complement is open, right? So this again contradicts our assumption, right? This is closed, I and J are closed. So it's not possible to write this when I, J are closed and satisfying these conditions. Okay. Yeah. Now, as another question, like, um, again, true or false? If is square root of p is irrational if every for any prime p, right? So it is irrational actually. So as a detailed proof, we can go over this now, and you can stop me wherever it is not clear. Suppose we assume that the square root of p is rational. Rational means we can write square root of p as ratio of two numbers, basically integers, positive integers, such that r and s have no common factors. If there are common factors, you can cancel them, right? So I guess up till this point it's clear, and this is important. R and S have no common factors. Okay, and now this is same as this, right? This thing is same as this. Then just rearranging things, we get r square is p times s square. So what does this mean? This means that p divides r square, right? Because you are able to factorize r square as p times s square, right? So p is dividing r square, which means p divides r. Why this is true? Because if any prime number divides, say, a b product of two numbers, it has to divide either a or b, right? There's a result, right? So using that, it has to divide r. So again, when we know this P divides R can be written as some P times T, right? This R can be written as P times T for some T. Then again, we can do this, right? By square, doing the square, R square is P square times T square. Then we equate both these things, right? Now P square T square is P square, which implies that now S square is equal to P times T square. What does this mean now? This means P divides S square because S square is factored as a product of P times some other T square, right? When P divides S square, by the same logic, P divides S. Okay, now P divides R. Now we obtain P divides S. So we obtain P as a common factor of R and S, which was against our hypothesis that R and S have no common factors. Okay, so that's why our assumption was wrong that it is rational. That's why it's irrational. It's a proof that works for any square root of P or anything. P can be anything, any prime basically. So the factor that the prime was used is here. Okay. Any questions on this?
No.
Okay. Yeah, again, as a set, right? So minus 1 by n plus 1 plus minus 1 whole power n times n square, set A, and set B, x square is less than 9. So let's, because set B is simple to see, uh, what what do you think is the correct? It's bounded below or not? Okay, so x is what? X can take numbers, can only take numbers from minus 3 to 3, open minus 3 to plus 3, right? So it is bounded below by minus 3. Anything less than minus 3, this condition will break, right? So this is bounded below. Now what about A? A you can split like this, right? As a sequence, minus 1 by n plus 2n square when n is even, minus 1 by n when n is odd, right? Just because if you see n is odd, this gets 0. Now, first of all, is this sequence bounded? Bounded above? No, right? Because as n tends to infinity, this will the even part will end up going to infinity. But then this sequence is bounded below because every other number is bigger than minus 1, because you keep adding minus 1 plus something, right? And this will also goes to 0, right? Which is again greater than minus 1 as n increases, right? So this is the key reason. So both A and B are bounded below. Okay. Is this clear? Is this clear? We can go to the other one if this is fine.
Yes.
Yes, sir. Yes, sir.
Okay. Now again state if this is true or false. Now S and T are two subsets of real number, non-empty subsets such that S union T is R and S is less than T for all S belongs to S and T belongs to T, right? That means the set S is upper bounded by every element of T. This is what it means. This is what this statement means specifically. S less than T for all S belongs to C and T belongs to T. Okay. And then there exists a unique beta such that for every S belongs to S is less than beta, and for every T belongs to T is less than beta. That means there is a cut. If this kind of thing exists, then there exists a cut such that all the elements in S is less than that cut element, and all the elements in T are greater than that cut element. Is this true or false?
True.
Um, I don't think so. Um, it's true, but do you think the cut element can belong to the set S or T? But the it has to belong to either S or T, right? But then if it belongs to either S or T, it you cannot satisfy this condition. So this beta, as when they say this is uh, so beta belongs to R, that means it has to belongs to either S or either T. Now if it belongs to S, you can't write just less than, you have to write less than or equal to. If it's same thing with the T, if it is T belongs to T, it has to be greater than or equal to. It cannot be strictly greater than. Do you agree? Okay, so what I'll do is in the next slide, I'll go over the proof that such an whenever this happens, okay, this happens. Um, so basically what we'll prove is this. ST subsets of R, just ignore this thing, or maybe you need it. Okay, let's assume this is there, and there exists an element beta which satisfies this, that we can show. Okay, so S is less than T, right? For all S belongs to capital S, is a typo. we conclude that S is bounded above and T is bounded below. So supremum of S exists and infimum of T both exists. Again, it is one can see that supremum of S is less than or equal to infimum of T. Okay. Now, the thing is, let's assign some names here. Alpha is supremum of S, gamma is infimum of T, right? Now ideally we want to show that this is the same, right? Supremum of S is equal to infimum of T. So we consider a case where this is less than gamma. It's strictly less than this, right? Now, if this is the case, this is the case, you can always find a U which is lying between alpha and gamma. Okay. Now this means S is less than U for all S belongs to S, and U is less than T for all T belongs to T, because T is greater than or equal to gamma and S is less than or equal to alpha. That's what this definitions tells us, right? But what's happening here is the union of this S and T is yeah, because we are given that union of S and T is R and you cannot find a U. Um, now you found a U that is not belongs to S and T, right? So that gives a contradiction. So this both has to be equal, right? So yeah, I think this can be true if one of this is greater than or equal to. Otherwise, I doubt if we can say this is true, right? If beta belongs to R, it has to belongs to either S or T. I mean, existence is fine, the proof is fine of such a beta, but then um, this is what is a bit uh, problematic. Okay.
Okay, sir.
Yeah, I think this is the last question for this thing. Okay. So this is in closed minus n to n, and this is jn minus 1 plus 1 by 2 power some n plus 1, 1 minus 1 by 2 power n plus 1. So basically what is happening is this capital INs are increasing, minus 1 to 1, minus 2 to 2, minus 3 to 3, minus infinity to plus infinity, is covering entire real line. Okay. Jn, what's happening? Let's say what happens at n is equal to infinity. This will be 0, but it's not exactly 0, right? So this is what it's like, you know, it will become minus open minus 1 to uh, open plus 1. Okay, so this is increasing from minus 1 to so on minus infinity to plus infinity. This is increasing from, I think, what is happening at n is equal to 1, minus 0.5 to plus 0.5. It is increasing from minus 1 to open minus 1 to close minus 1. Okay, yeah, I can see, right? I becomes R and J becomes minus 1 to 1. Now we can see, is R closed? R is both closed and open. Okay, entire real line is both closed and open because it satisfies all the definitions of the open set and closed set. Because every point of R is an interior point and R contains all its limit points also. Okay. J is not closed, right? Because J is open -1 to open -1 to +1. And yeah, so this is the correct option. But can a set be neither open nor closed? Do you know that? Can you construct a set which is neither open nor closed? That's very easy, right? I mean, -1 to +1. I mean, you can put a closed anywhere, either on -1 or +1. Okay, so this is neither open nor closed, right? This. Yeah, I think that's all I have for the today's problem solving session. If there are any doubts, we can go over, or any questions or anything you want me to explain, I'll try. Otherwise, I think, yeah, any questions?
No, sir.
Okay, then. So we can meet next week. That's it for today's tutorial. Bye.
Thank you, sir.